Hello everyone, hope you're having a great day. Today in my lecture we're going to be going over thermodynamics. I'm going to be reviewing some class material. I'm going to be going over the three laws, which you should already know. I'm going to be going over some examples of the laws in real life. I'm going to be going over how entropy is always increasing in the universe. That is one of the three laws of thermodynamics. We're going to be going over real life applications, and then I'm going to be going over thermodynamic processes and cycles. Now starting off with thermodynamics review, starting with internal energy U, we have that the change in internal energy is equal to the heat added by the system subtracted by the work done by the system. The enthalpy H, the change in enthalpy is equal to the change in internal energy plus the change in either pressure or volume times either pressure or volume. And then entropy, S, is equal to Kb times ln of omega. Kb is a Boltzmann's constant, which is equal to the gas constant divided by Avogadro's number. And then omega, the number of microstates, at the spatial and energy levels. So microstates are possible arrangements of a molecule which tend to increase with temperature. And then another formula for the change in entropy, which is equal to the change in heat divided by the temperature. And then Gibbs energy, the change in Gibbs energy is equal to delta H minus T times delta S. And the reason why that's important is we can tell if a reaction is spontaneous in the forward direction, or say a process to be spontaneous in the forward direction. Now moving on to the three laws of thermodynamics. The first law is that energy is always conserved in the universe. The second law is that the total entropy of the universe increases in every spontaneous process, which is a pretty interesting statement, at least in my opinion. And then the third law is that entropy is minimized as temperature approaches absolute zero. Another law of thermodynamics, which is sometimes referred to as a zeroth law or as a fourth law, is that if two bodies are in thermal equilibrium with a third body, then the two original bodies are also in thermal equilibrium with each other. Now here are three examples of these thermodynamic laws in real life. So in terms of the first law, each and every single of these, energy is conserved. Energy is always conserved no matter what. So for heating up the kettle, so any heat that is lost, that dissipates into the atmosphere or the surrounding areas. So the energy still exists, it's not in the form that you desired it to be. And then in terms of the second law, entropy of the universe increases in every single spontaneous process. Freezing water into ice cubes when it's the winter time in Kingston, that's a spontaneous process. And melting an ice cube during the summer in Kingston, that's also a spontaneous process. So that should lead to the entropy of the universe increasing in both of those processes. Now in terms of the third law, since entropy is minimized towards absolute zero, as water freezes into ice cubes, the entropy of the water decreases. Now the second law of thermodynamics states that the entropy in the universe increases for every spontaneous process. Now I found this to be a shocking and surprising statement, but one of the things that helped me to understand why this is the case is that entropy increases when more energy is spread out evenly in a substance/space, and energy naturally tends to spread out as much as possible. So using that fact, we could come up with these three facts below. That firstly, the universe had minimal entropy at its conception or when it was created. And this is because the energy wouldn't have had time to spread out evenly. So the entropy wouldn't have been increased by much. The entropy of the universe has never been higher than right now. This is because, well, the energy has been given more. There's never been so much time for all the energy to spread out evenly within our universe. So then entropy has increased. And then the universe will reach its maximum entropy right before it ends, which is because there'll be even more time for all the energy to spread around evenly. And then another thing you can consider is that, say, stars like our sun, they're gonna explode, and all the energy from the sun and all the other stars, they will start dissipating into the universe, so that eventually almost every single point in the universe will be at about the same temperature. Thermodynamics are crucial in modern society, and we take their applications for granted, and oftentimes we don't even think about it. So one of the applications is heating our houses, which almost everyone has in Canada, creating computers that don't overheat, and we're all watching this video. Everyone who's watching this lecture is using a computer. If it overheated, that would be a big problem. And engines for transportation devices, we rely on these kinds of devices all the time. How are you supposed to get from one city to another unless you're going to be running, which isn't feasible for long distances? Cooking food, which is, even say if you're cooking it with a fire, a natural bonfire outside, that still relies on thermodynamics, although you don't really need to understand the thermodynamics to cook the food, although you can take advantage of understanding the thermodynamics. And then a very important application are power plants, because this is how we power, say, our houses. Almost all of our houses are ultimately powered from power plants. So the three laws of thermodynamics can be applied to almost anything. Here on the screen, I have listed 6 different thermodynamic processes. So starting with an isobaric process. An isobaric process is a process in which the pressure stays constant in the system, whereas an isochoric process has constant volume. An isothermal process has constant temperature, and an adiabatic process is a process in which no heat is transferred to or from the system. A quasi-static process happens slowly enough so that the system can stay in an internal equilibrium, and a reversible process is a process in which you can start at a starting point, you can go to an ending point, and then from that ending point you could go back to the starting point with the exact same conditions. And during the reversible process, the system is in a thermodynamic equilibrium with its surroundings. Now here on the screen, as you can see, I have a couple different diagrams of a Rankine cycle. I'd say the diagram on the top right is probably the easiest one to help understand what's really going on. I'd say that this one in the bottom left is kind of confusing, but a Rankine cycle is an idealized thermodynamic cycle which converts heat into mechanical work. It's known as a cyclic process because the state of the system is the same at the beginning and the end. The Rankine cycle has been used as a model to predict how well a steam turbine system or a reciprocating steam engine would work. The Rankine cycle is commonly used in power plants such as nuclear reactors and coal power plants. It makes use of isobaric heat transfer and the isentropic process, which is an idealized thermodynamic process that happens to be adiabatic. So here on the screen you can see a Brayton cycle, which is also known as a Joule cycle. So this cycle is used in modern gas turbine engines and jet engines. So Brayton type engines are made up of a compressor, a mixing / combustion chamber, and a turbine / expander. So the pressure volume diagram and the temperature compared to the entropy diagram are examples of a real gas turbine engine which had its pressure, volume, temperature, and entropy recorded. So as you can see, from certain points you'll have constant pressure. So say from step 2 to 3 you'll have constant pressure, and then here the temperature will just go straight up when the entropy is constant here, from 1 to 2 and then from 3 to 4. So an idealized Brayton cycle, the 4 steps consist of, firstly, an isentropic or adiabatic process happens and the ambient air goes into the compressor, which then pressurizes the air. Secondly, an isobaric process takes place and the compressed air goes through the combustion chamber, which is heated by a fuel. And then thirdly, an isentropic process again, which is adiabatic, takes place and the hot pressurized air loses its energy. And fourthly, an isobaric process takes place in which heat is rejected, the exhaust gases, in other words, are released. So in an actual Brayton cycle, which is quite similar, the first step would be an adiabatic process in which the fresh air is compressed. And then secondly, an isobaric process takes place and the heat is added. And then thirdly, an adiabatic process takes place and the compressed air expands. And then fourthly, an isobaric process takes place in which heat is rejected, so the exhaust gases come out here, and then there is work coming out. And thanks for listening, and here's some of my references.